Hello and welcome back to Differential Equations, section 2.2, General Solutions of Linear Equations. So we know that the order of differential equation depends on its highest order of the derivative. So if you have the fourth derivative show up, you would say the equation is the fourth order. If it's only first derivative there, then it's the first order, and so on. Last class, we take a look at the second order. It was like introductory. The next class will do the same, second order. Today is more of a general talk. So whatever we saw last time, we are now going to extend to any order, write down all of the technically same conclusions, and learn how to put these solutions together, and also learn how to check the solutions. So some of you might be interested in the solution in terms of whether it's right or wrong. So we start with the principle of superposition. Well, actually, maybe I should write the equation. I still can. So the nth order equation, maybe purple. So the nth order equation, P0 of x, so it can be a function or a constant there, y to the nth. So you know that you, for the first derivative, use a prime, for second derivative, 2 primes, right? And then third derivative, 3 primes. When you reach fourth derivative, you start writing derivatives like that in parentheses. That's the notation. So that's why we have n in parentheses there. Plus p1 of x, y to the n minus 1, that's one derivative down, plus as many of these as we need to have, p to the n minus 1 of x, y prime, plus pn of x, y equals to f of x. And then we learn the homogeneous and non-homogeneous, which is all still there, depending whether that f of x is 0 or not. So homogeneous would be when it's 0, non-homogeneous when it has some kind of forcing term. Now, we also learned that these nth order equations, at least for the second order last time, that it will have these two separate y1 and y2 solutions, which could be linearly dependent, right, or independent. And then we learned the principle of superposition, which said that you can actually multiply them into constants and add them together. So we are going to have a principle of superposition for homogeneous equations, where we take all of these y1, y2, y3, yn answers and multiply them by constants and add them all together. So your answer would be, and this is in theorem 1, definitely allergic to someone in here. No, I was sneezing before you showed up, so only you and Kyle are safe. The rest of you, I don't know. I'll have to figure out. Well, those of you in Calc 3 are safe as well. So, yeah, I know. Kind of trickled down to 3 of you. There's 7,000 people in this room, but I know a lot of people. All right, so let all of these y1, y2, y3, all the way to yn be n solutions of the homogeneous linear equation. when I say linear ODE, ODE stands for ordinary differential equation, as opposed to partial or others. On some interval I, if C1, C2, C3, Cn are constants, then the linear combination y equals C1 y1 plus C2 y2 plus C3 y3 plus dot 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 Cn yn is also a solution to the same ODE on I. So in the process, let's say you have a third order equation, so third derivative. You come up with three answers in this case. Y1 equals, I don't know, e to the x, and then y2 e to the 2x, and then creatively y3 equals e to the 3x. You can put them all together into the same answer. So so what this theorem is saying is that if y1 is equal to, let's say, e to the x, y2 is equal to x squared, and y3 is equal to, I don't know, x sine x, it doesn't matter what they are. And they're all solutions to a differential equation. You can write y of x is equal to c1 e to the x plus c2x squared plus c3x sine x. And that thing is going to be the general solution to the equation. Now, given initial conditions, enough of them, you will be able to figure out C1, C2, C3. Now, if you have many of those, clearly you will be getting systems of equations, so you can use matrices or whatever other witchcraft you know to come up with the values. Existence and uniqueness also carries over from second order to nth order. We are going to have solutions to obviously exist, and then to be unique in sense that given initial conditions, there's only one possible answer, which is a function, right? Now, a lot of people are a little bit confused on this uniqueness part and why it's such a big deal. Well, and what it means actually. So if you go with a basic equation, x plus 3 equals to 5, you know that you are supposed to subtract 2 and get x equals to, subtract 3, and get the answer is 2. That's the unique solution. Obviously exists, it's right there, you can see it, but it's unique. It's guaranteed that you're not going to get also x equals to 1.3 or 107 at the same time to solve this equation. This solution of x equals 2 is unique. So now when you go a step in magnitude higher, and you, instead of these algebraic equations, you have differential equations, their solutions are functions. And uniqueness and the uniqueness guarantees that function you get, particular function you get, is the solution for your equation. So suppose that the functions p1, p2, pn are all continuous on the open interval containing the point A. Then given n numbers b0 through bn minus 1, the nth order linear equation has a unique solution and the entire interval, and then you have the conditions for the. So this theorem, I mean, we don't use this theorem to compute anything in this class. It's just for you to, right? Because if I ask you to solve differential equation, there should be a solution there, right? So it exists. Those of you interested in mathematics and so on, obviously, you will pay great attention to this particular theorem. We are also talking about linearly dependent and linearly independent solutions. How do we check that last time? Wronskian matrix, exactly. It had two, right? You had the row of functions, row of derivatives. And then if the matrix was equal to 0, then the solutions were linearly dependent. It's a 50-50 chance, right? Actually, no. When you have two things like that, it's and you add stress, it's like 70 to 30, right, in favor of actually getting the wrong answer. So yeah, if the Wronskian was 0 in our previous lecture, right, for second order, then we had linear dependence, and if it was anything but 0, equations were linearly independent, those solutions. And then you can put them together into one. So now we are going to carry this to higher order. And as we do that, what kind of matrices are we going to get? What happens if you have 5 solutions? It's going to be 5 by 5 equation to solve, right? So you see, it's going to get messy very quickly. All right, so linear dependence, and then we're going to add the Wronskian to it. So this one is definition, again, very important. The n functions, f1, f2 to fn, are said to be linearly dependent on the interval I provided there exists constants C1, C2, C3, all the way to Cn. Not all 0, such that C1 F1 plus C2 F2 plus dot 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 Cn Fn equals 0. So the linear combination will actually equal to 0. So that's the definition. Now we know that when we get dependent solutions, we fix them. I put the air quotation marks. So now, here also in red, we check for linear dependence. Using Wronski. And in a textbook, they gave you something to enjoy in terms of the. These are pretty good, but maybe we can. Maybe we can check. So how's the Wronski going to look like? Well, for 3, we have y1, y2, y3. So those are the 3 given. 1, 1 prime, y2 prime, y3 prime, y1 double prime, y2 double prime, y3 double prime. That's the Wronski setup right there. I don't think I ever used green, so there you go. But in all reality, guys, Wronski is going to be the determinant of y1, y2, all the way to yn, 1, 1 prime, 1, 2 prime, all the way to yn prime, and it's going to go down to whatever order of derivative you might think of, and then y1, y2, and so on. So this is the general kind of look for the Wronski for any dimension. Those dots, 3 dots or whatever I put, says this extends infinitely. Let me just see if the stream is. So the theorem says if y1, y2, all the way through yn are linearly dependent, then Wronski is 0. And if y1, y2, y3, yn are linearly independent, then the Wronski would be different than 0. Oops. Now, it's just figuring out determinant of the matrix, except you don't have numbers, you have functions to enjoy. So all of your brain power in terms of algebra and everything else needs to be used in these calculations. So how about you enjoy one of these to check if they're linearly dependent or independent? Because I see some of you are passing out right now. I've been talking too much. So you got this. Here's problem 10. How hard can it be? So are these linearly dependent or linearly independent? First function f of x is e to the x. Second function g of x is x squared. Sorry, it's x to the negative 2. And then h of x is also negative 2 times ln x. There we go. So check for linear dependence or independence, whatever the Wronskian gives you. So solving the determinant of the Wronskian, right, would be the same as, let's say, cross product calculation. We have the pen that it's not working again. Ah, it's partially working. So Wronskian would be e to the x to negative 2. Well, I'll put 1 over x squared. And ln x over x squared. And now we have its derivatives. How would you define a problem like this? Hard? Is that a good word for this problem? Tedious and annoying, exactly, that's all it is. So what do we have? Negative 2 over x to the negative 3. And then 8 over x to the, sorry, x cubed. So are these two good in terms of derivatives? Anyone? Because 2 times 3 is not 8. It's 6. I'm just testing you to see if you're paying attention. That's it. Now what do we do for this one? Exactly. Product or quotient. So we have x squared times 1 over x is just going to be x plus 2x ln x, right? We can factor out 1x. So it's x plus 2x ln x over x fourth. So when we factor out an x on top and cancel with 1 from the bottom, we're going to get x plus 2 x ln x. We need one more derivative. Maybe do that one on the side. So it's definitely over x to the 6, right? Or maybe not if something cancels.
Let's move the x to the 4.
Where?
Yeah,
The 4th?
right?
Yes. Yep. No, but it's x to the 3rd. Oh, because I didn't factor out this. It's supposed to say 1. Is it better? What do you mean you don't know? So all I need to do is to take the derivative ln x over x squared. So it's x to the 4th. I had it here and then I erased it. To the 4, copy x squared and then 1 over x minus the derivative. This is 2x ln x. So x squared will cancel 1 over x. You have x, but you have x here. You factor those and you cancel with this. So the answer is 1 minus 2 ln x. Are you happy with that? Who cares, right?
Isn't it x to the negative 2 though?
Where? Over here?
Yeah.
No.
It's next to negative 2 ln, which is h of x.
Mm-mm. These are your two guys. And now I have to do everything again with the one below. So copy as is times the derivative of the inside, which is just negative 2 over x minus 3x squared plus. And then we have the derivative going. So copy this one, the derivative of this one, copy this one, and then derivative 3. There we go. Can we kick out? We can kick out x squared. And then this becomes just negative 2 minus 3. What happened?
And then now later, 2 to the negative 5 plus 6 ln.
Where? When?
To the unit, the final thing.
Oh, negative 5? How'd you get negative 5? I should not even ask. It's like, yeah, we use Mathematica. You can just keep computing over there. So what was it? Negative 5.
Negative 5 plus 6 ln.
Okay.
Why do you stop it? Like, what's supposed to be going on until something turns into like 0? Or like it's not.
No, why? It's a 3-solution matrix. So 3 solutions, which means that the matrix is going to be 3 by 3. You have 3 solutions, and then you have their derivatives, and then one more of derivatives.
It's always just 3 by 3.
For 3, yes, but then you can have 7 by 7. If you have 7 solutions, and then only 7 derivatives involved. I've never seen past 4th derivative for application, ever. So you're good with knowing that too, right? All we need to do is to put this thing together algebraically, which is going to take another 8 years, right? Because when we do when you do the what's it called? Determinants. There we go. You delete the row and a column. So whatever you circle, whatever you circled is the one where you start, and then you have negative 2 over x cubed minus a 6 ln x over x to the 4th. So you have those that are multiplying minus 6x to the 4th times 1 minus 2 ln x over x cubed. So that's the first term. And then you simplify that algebraically. And then you repeat for this term, repeat for that term, picking off of the line that is killing the row and a column as soon as you pinpoint which one you want to do. So now, all of this, right, would be, oh, here's the killer. You gotta put the minus sign for the middle column. So I'll put that in red. Minus And now we're doing it again, like this. Hey, so here. So I have minus 1 over x squared, and then we have e to the x times this. So I'm going to factor out e to the x as well, and keep it as 1 minus negative 5 plus 6 ln x divided by x to the fourth. Okay, so that's that. Minus e to the x I kicked outside. 1 minus 2 ln x. Sniffling. 5x cubed. This is a fourth. It looks like a 9. And then finally plus ln x over x squared. Don't want selections, it's just giving me. Okay. Ln x over 2, over x squared. And then we have these 4. Kick out e to the x as well. And what's left is 6 over x to the fourth minus e to the x is pulled out. So what do we get? Anyone? Exactly. And then you perform this algebra, make sure it's not 0. So you clean it up, you distribute everything and so on. I don't want to waste the entire class on it. But you see that it's far more complicated and far more annoying if you have the 3 by 3, and then just imagine, how the 4 by 4 looks like it's done on the exam. I mean, not on the exam. No calculator either. It's burned all the time. Good. So that's the part on Wronskian and solutions being linearly dependent or independent. Now we are going to learn, this is going to be a major point, guys, if you get those repeating solutions. Depending on what type of differential equations we are solving and depending on which type, what type of solution is, what kind of function, you will be remembering / memorizing what are you supposed to multiply into that solution to make it linearly dependent. You can't multiply anything because it has to work, but there are fixes. The last part of the lecture is on solutions to non-homogeneous equations, which means that now you have a forcing term. Again, we're not learning how to solve any of them right now. It's just like here. X equals to 2. Now understand it. Okay? That's technically what we're doing now. So you are so far used to solving differential equations. You get equation. You get, let's say, y equals to 3x, and you're done. Sure, for homogeneous case, separation of variables works, everything technically works, it's awesome. But what happens if you constantly have some kind of driving force for the system? You remember when I was pushing kids on a swing, right, the example? So what's that forcing term? It's your push. every time, right? So periodically, you can literally take that motion and think of it as a sine cosine motion, because sine cosine would do like this, right? So if I push this way, I'm applying peak, nothing, nothing, peak, nothing, nothing, which is me pushing as well, right? The impulse function, delta function, something like that happen, or just, leaves and be boring like a parabola. That's it. So these guys, these creatures, they're non-homogeneous equations. They have a forcing term. They are going to have still the same base solutions like homogeneous one when it's equal to 0, but then they'll have more stuff. And that more stuff we call the particular solution. And then we add them all together into one giant final answer. So let's talk about non-homogeneous equations. I'm just going to say do this on Sunday. Finish this on Sunday. And if you're working on Sunday, just do it tonight. Right. Yes, for sitting in circuits. So now you have that y of n plus p1 y to the n minus 1 plus a whole bunch of these dots, and we get a p n minus 1 index of x y prime plus pn x y equals to f of x. And the word non-homogeneous here alerts to that this is not 0. That's what you learned last class, if you got to the point where you're learning. All right. So now the solution is going to break over two parts. There's going to be the solution of so it's like a general solution, and then there's going to be particular solution, and then you put them together into the solution to the equation. Now, I'm just trying to see if they have nicer, yeah, they don't. Well, I'll write it in blood anyway. So, what do I want to write? You're supposed to be very important in red. Is anyone paying attention? 7,000 people in the classroom. So the overall solution y of x is going to be the it's going to have two parts. Now I'm trying to see, yeah. So actually, complementary solution goes first. That's we are used to. Complementary first and then particular later. I'm going to box this because this is how your solutions are going to look like. You will solve differential equation ignoring the driving term first. In my mind, it just sounded like Schwarzenegger to myself. I don't know if that actually came out that way. I'll have to rewatch the stream. So this part here is called a complementary solution, and that one comes from you completely ignoring the driving function, solving the differential equation as if it was equal to 0, homogeneous, and that's what you get. That now, depending on how the equation looks like, that part might have 2, 3, 15 terms. Then you jump to the second part, and you work out on the particular solution. So this one is complementary part of the solution. And this is particular. Solved. Awesome. Now again, linear combination of both works. Now you also have the constant C1, C2 floating about because, as I said, guys, this could have as many as you want, this could have as many as you want, but each one over here in YC should get C1, C2, C3, and so on. So you can expand everything you want. The textbook went all the way out to solve 3x3 system using, systems of equations, real quick. Okay. So we're going to take a look at some examples. Again, we're not learning, we're more learning words over here, meaning stuff, making sure that stuff works before we start doing it. We're going to start working on problems and sections that actually solve equations next class. So 2.3, everything I said last class will be repeated and then added on it in terms of how the solution looks like and, what it do. For now, what they give you is they give you the differential equation, they give you the solutions, and all they want you to do, which is more than anything else, take derivatives, plug them in, check that those are actual solutions. So that's one part. Or they have a question where you actually have to figure out the constants, which means system of 3x3 at least equations, and then go from there. So let's do some of these messy problems, trivial but messy problems. I've got the thing. So problem 7 to 12 use the Wronski now. Again, check the Wronski, sure. A non-homogeneous differential equation complementary solution YC. Okay, so here's the one. So these are 21 through 25. Now, as I said, they're giving you solutions. They're just teaching you here how to put solutions together. We're going to start solving equations next class. Any one of these is fine. Let's try 22. Try. Do or do not. There is no try. Y double prime minus 4y is equal to 12. Y of 0 equals 0. And y prime of 0 equals 10. They're giving you the solution yc c1 e to the 2x plus c2 e to the negative 2x. Yp, particular solution, is equal to negative 3. So how do you do this? How do you put the solution together? Actually, when they gave a solution initial conditions, the function up there, I will. But anyway, what do? They gave you technically three solutions, right? You have the C1 and C2 terms, and then you have the yp is equal to -3 on the side. So what's happening there? What are you supposed to do? What is your goal? The goal is to find particular solution. What do you mean?
12 plus leave it over there.
12? Oh yeah. Well, you don't have to do any solving here because they gave you solutions already. This problem is just for you to put the solutions together. And that's what I said, you don't even need this thing. Unless you want to check if their solutions make sense. Like e to the 2x, the derivative of e to the 2x will be still e to the 2x, and this is going to be e to the 2x, so the coefficients work out again. I'm done. Right. So yeah, we can check each one individually.
Take the derivative first, the second derivative.
Yeah, all we need to do is to take the derivatives and plug this in. We already have the yc, which is this plus yp. It's a superposition. So to solve this, we have the general solution of x. So no c, no p now. c1 e to the 2x plus c2 e to the negative 2x minus 3. I mean, if we could just write this as 2 cosecant hyperbolic x minus cosine hyperbolic 2x minus 3, life would be much easier, much less writing. We can, but yeah.
How because of the c's?
No. Yeah. If the c works out to be the same number, then yeah. Because then you can factor it out. All right, so and we need the derivative of this puppy. So y prime is equal to 2c1 e to the 2x minus 2c2 e to the negative 2x, and that's the end because the derivative of negative 3 is 0. So now this is the solution already, right? This is its derivative, and I think we have to take one more derivative, right? No, that's it, because look at the conditions. The highest condition is the first derivative. So plug in 0 into the first one. I'll say plug 0, 0, because we want 0 on the other end. So 0 is equal to, which one was the one? All right. So plug everything in, guys. It's C1 plus C2, right? That's what I said. And for the second one, plug in what? 0, 10. So now we plug that in the derivative. 10 is equal to, we know that this guy over here is 1. And we know that this guy here, how much is, this is 10. 10 is equal to 2c1 minus 2c2. All right, solve the system, and we're good. C1 plus C2 is 3, and if we cancel here, C1 minus C2 is equal to 5. So now you can either, whatever witchcraft you know, solve this system. Separate, elimination, or guess and check factor, whatever. So now we simply add these. C1 is 4, and C2 clearly negative 1. Once you plug C1 and C2 where they belong, it goes right there. C1 and C2. Whatever, 4 and 2, whatever. All right, that's that. It's called efficiency. Maybe you should try one of these. That's going to take forever. They want you to show the linear independence for the third order. All right, so try this on your own, see how it goes. So y triple prime minus 6y double prime plus 11y prime minus 6y equals 0. Conditions that you're going to need to compute those constants are y of 0 equals 0 and y prime of 0 is also 0. Wow, that doesn't work. Now the solutions, it's also y prime of 0 is 3. So now y prime of 0, double prime of 0, yeah, so these are solutions. You just put everything on a pile in the book. It's so difficult to read. All right, so y1 is equal to e to the x, y2 is also e to the x. No, it's e to the 2x. y3 e to the 3x. Put the solutions together and then use the matrix or whatever else, guess and check method, to figure out C1, C2, C3. So where would you start this problem at all? What would be the first step? Yeah, write down complementary and particular solutions and put them all together. And you have all the complementary listed. Now, is it going to be a particular solution? No, because homogeneous equation, right? So we're not going to have the yc plus yp this time because it's homogeneous. But then it's a third order, so 1, 2, 3 solution. Now, as you're doing this, in the field, the order of the steps, right? The ordering would be to first check that they're linearly independent, and then go on to stuff. I lost this mean, I just can't get, it was awesome. 3 rows of, I think I told you that in class, about exact equations. 3-row expression of crazy mathematical function. And, you're supposed to find the potential function for it. But the idea said, there was a troll face that said it's not exact. Right? So, there's order to all of these things. You sit down, you learn it. And the order says, I wrote this one twice, so I'm just going to erase it there. Here are your initial conditions. Here are solutions. So C1, boom, C2, C3, add them all together, differentiate. You have 1, 2, 3. 1, 2, 3. System of equations, done. I need this written twice. So for the rest of the chapter, it's going to be us figuring this out, right? That's how you upgrade. So right now your solution is given, you just need to figure out how to put it together and compute C1, C2, C3. Alright, so go ahead, about 19 seconds or so. You have the same system like I do? At least so far. All right, good. So what we need to do now is to solve the system. How do you solve the system? Matrix, okay, and do the matrix. You can eliminate C1. Yeah, Gauss elimination. You will eliminate. So if you subtract, let's say, first two equations, so equation 2 minus equation 1, you will get 2C2, so it's just C2, C2 plus 2C3 equals 0. And if you subtract third equation minus second equation, you will get 2C2 plus 6C3 equals to 3. Now you multiply the top equation. So now top equation by 2 and then subtract again. So you can go equation 2 star minus 2 times equation 1 star. So that will eliminate C2. You would have 6 minus 4 is 2C3 equals to 3. I got C3 to be 3 halves. Is that what you have, guys? 3 halves? Well, let's check. So 2 minus 1 C1, 1 C2, and then 2 C3s equals 0. And then equals 3. That's gone. That's 2 C2s and then 6 C3s. Good. Now that becomes new equations 1 and 2 with the stars. So second equation minus first, but the first I have to multiply by 2. So that's gone. 6 minus 4. Yeah, I think 3 halves should be good. Sorry. So now we plug in C3 into this equation here. That's just going to be 3. So C2 is negative 3. And I need to add to 0. So what do I have when I add these two? 3 halves. I get negative 3 halves. Negative 3 halves for C1. No. No, I give up. So it's positive 3 halves. Because 3 halves plus 3 halves is 3 minus 3 is 0. Awesome. So what is the actual solution? It's C1, which is 3 halves. What's the first one on the list? E to the x, e to the 2x, e to the 3x. E to the x plus, no, minus 3 e to the 2x plus 3 halves e to the 3x. That will be the solution. That's all we are talking about today. How to put the solutions together, and again, how to figure out these, not how to figure out the actual answer. So all of your homework, everything is given to you. You just need to figure out how to put it together. Now, starting next section, we will be solving differential equations, which means that you will learn how to come up with all of those E solutions and on. Just don't miss next class. Don't miss Thursday. Thursday is going to be good, and we're going to set up, like not a standard, but we're going to set up a particular thinking on how these things are done. Let's say it that way. So see you all on Thursday. Bye, stream.